we just took a look at the graphical model for Bayesian linear regression. And it looked just like this thing. We wrote it all out, and then we used this plate notation to sort of compactify it and roll all these up, or stack all these duplicated sort of entries up into this box here. And next, so that was a really good warm up for our next example, which will be Bayesian naive Bayes. We'll look at the graphical model for Bayesian naive Bayes. So I'll give you the generative process description for Bayesian naive Bayes. It's of course the classification setup, right? We've got, let's use some color here. We've got our data x1, y1. It's again a supervised learning problem, and the xi's are some vectors. Let's say that, they're just d-dimensional vectors, but for simplicity, let's say they're in Rd, and the yi's are just from some finite set of classes which will number from 1 to m. And the probabilistic model that we will take for this is the following. We will take pi to be a random variable with some, I won't write it all out in detail, but this is going to be, well, maybe I will. So this is going to be Dirichlet distributed with some parameter alpha, and then we had all these R, J, Y distributions, and they were all Dirichlet with parameter beta, and this was for J equals 1 to D, one for each of the dimensions, one for each of the features of X, and for all Y in 1 to M. And these were defining the conditional distributions for xj given that y equals that value of y. So each of these was a conditional distribution, and this was a distribution on the classes. So here pi, maybe I should put just alpha, was in Rm, and its coordinates are all positive. And beta, same sort of thing, except I guess, well, I won't write beta explicitly. We did that earlier. So let me just, well, just this is just to remind you of the model. And then we modeled y. So we'll just take for a generic x and y. Let's look at the distribution for a generic pair x and y. Y was distributed according to pi, and xi, or let's say xj, the jth feature of x was a vector, and the jth feature was distributed according to rj capital Y. So this little y is set to the value of capital Y, whatever y happens to be. So y is the class, and xj is the jth feature. And then we took, so that was for a generic x and y, and maybe let's add for each of the points, for each of these, I guess I should put, well, not yi, y sub I should have put here, this should have been superscripts following our previous convention, x superscript 1 up to x superscript n, and that's xi. So yi is just the same, and xij is just like this, yi. Okay, so this was the model description, the probabilistic model, and the way I defined it here was in the order that you would use to define it, using the generative process sort of convention. So I defined each of these things, and then I defined them in terms, I defined their distributions in terms of the previously defined random variables. Let's get rid of that. So what's the graphical model for this? So let's write it down. We have pi, and it had this little, let's go ahead and use the convention. of using a dot for a parameter, alpha. And then we had these RJs, but let's go ahead and put Y here. I'll sort of draw it in order. Y, maybe I should go ahead and put the RJs. So we had R1, 1, and then we just stack up. So then we had like R1, 2, and R down to R1, M. And let me just say, like, draw these as like a stack of, I'll just sort of maybe a list there. So just some sequence here of R's, R1, 1 down to R1, M, each of these. And then we had R2, 1 down to R2, M, and so on up to RD, 1 down to RD, M. And now you can probably start to see where the plate notation is going to be particularly useful. This will be a further motivation for the plate notation. So Y, let's just keep it the generic Y for now. X, 1, and this is the first coordinate, maybe I should say, to be explicit. X, this generic, well, I didn't put X here, but each of these coordinates is wrapped up into some vector X. And then we have X2 up to Xn. Maybe I should have put here to be more explicit. I should have put, I sort of left it out, where xi through xj through xd are independent given y. So I left that out. I should have put that here. Each of the features are conditionally independent given y. And that's what this represents. I only have an arrow from y going to each of the x's and not arrows going between them. We do not have that. There's no arrows like this. And of course, each of these x's depends on all of these guys, right? For each of these down here, it depends on all of these distributions, because when y takes the value, say, it could take the value 1, 2, 3, 4, so on up to m, and the value that x takes is going to depend not only on y, but also the distribution that the conditional distribution that y sort of selects here. So there's a bunch of arrows there. So now I think you're starting to appreciate, maybe you are starting to appreciate where the plate notation is going to come in handy. And of course we also have this beta parameter, which goes to all of these. Oh, sorry. Parameter for the prior, the Dirichlet prior, on each of these distributions. These were all categorical distributions. Okay, so that is the graphical model. And this model, the distribution for Bayesian naive Bayes, respects this graph. This is the graphical model for Bayesian naive Bayes. And that looks kind of ugly. That looks a little bit, well, it's not too bad. At least we could draw it without lots of overlapping things, but let's simplify this down a little bit. We can simplify this using our plate notation. So let's do that. So this is a good motivation for why plate notation is nice. So let's redraw it using plates. So we have switch color. Let's use a color. So we would again just have pi, of course. Oh, and actually another reason why we need plates is because now we weren't even done yet. That was just for one. But we have all these pairs, right? We have all these pairs, x, I, yi, as I goes from 1 to n, and we were using these to model our data. So we weren't even done yet. We then needed to have, for each data point, we needed a plate here. I'll put a plate here. we needed to have n copies of this, one for each I. So now let's do the whole thing in plates. So okay, so this is now the plate version. We have alpha, we have pi, we have y. Let's do the generic one first. The generic x and y. We have, now we can use a plate for the, well, let's not use a plate for the x's. Let's keep the x's separate. Up to x, x1 up to xd. Let's use a plate now, though, for the r's. So we have a plate here, r1, y. So y is ranging over 1 to m. So we have m of these. And we have one of these plates for each of these each of these dimensions. So it goes up to r dy. And there's m of those. So that's simplified things down quite a bit. And we can put beta. Let's go ahead and put beta here. And now let's put the plate in for each of the copies as I goes, for each of the data points. So we had I, xi, 1 up to xid, yi, and we have this plate. And I goes from 1 to n, put n here. And we could do one more if we wanted to also include the generic point for making future predictions. We could also add this one. So this was modeling our data, and this would be for if we observed a new x and we wanted to predict the y for that new one, we could use this. Well, let me do it this way. I guess it starts to get a little ugly now. Like that. So this is just one more copy of this. You could add like an I equals, you could make this like I equals 0 and just throw it in here or something like that. That would simplify things up a little bit. And now, so right, that's using the plates, and going back to before, we also introduced this notation of conditioning on the random variables that we observe. So what's observed here? In linear regression, we observed the values of the y's. That was the values that our data took. And now in Bayesian naive Bayes, what do we observe? Well, we observe the data, of course. We observe these xi's and yi's. So we can let's draw what's conditioned on. So we condition on our data. All these, xi, yi. And all these others, this is a latent variable. These are all latent variables. Latent or hidden variables. And I guess if we got a new point and we were predicting a y, these x's would also be observed. That would be the new x that we got and we wanted to predict a y for. I guess I didn't draw it here. But that would be if we got a new x and we wanted to predict the class y corresponding to the new x. So this is the graphical model for naive Bayes. And I think this is a nice example. This is a good example of a sort of something approaching a realistic, real sort of real world application of graphical models. So this is a nice example.